Thank you, Mr. Chairman, for the presentation. This presentation, deals with the various cycle fatigue behavior of materials, and in particular with the crack growth in the various cycle fatigue. Indeed, it is well known that failures at varying number of cycles and at low stress amplitude are possible. And in particular, high-strength steels are prone to various cycle fatigue failures, with a crack originating from internal defects, and with a particular fracture surface morphology, which is called fisheye morphology. Different theories have been proposed in order to justify the crack origin in various cycle fatigue. In particular, researchers are trying to understand why the crack can grow also even with a stress intensity factor associated to the initial defect, which is below the threshold for crack propagation. So the objective of this presentation is to propose a general macromechanical model for crack growth in the various cycle fatigue region, and consequently to define a model for the fatigue limit from inclusion and defect, which can be used for the design of components. Let's start with a short introduction of the fisheye morphology. Here we report a fisheye morphology that we obtained in our lab. With naked eyes we can recognize two features, a zone of final fracture and a zone on crack growth, which can be subdivided into two zones, a rapid crack growth and a steady crack growth inside the fisheye, which is shown in the figure. In the center of the fisheye, we can find a fine granular dark area, which is called fine granular area, FGA by Sakai, and is called with other denomination by other researchers who work in this field. At the center of the fisheye, we can see, by using the scanning electron microscope, the initial defect. In this case, it's a non-metallic inclusion, but it can be any type of defect which is present inside the material. The most characteristic peculiarity of this of the various cycle fatigue failure is that crack can grow from the initial defect with a stress intensity factor which is below the threshold for crack propagation, and this is in contrast with the linear fracture-elastic mechanics theories, the common theories. So a number of different theories we propose to justify this strange behavior. For example, Sakai proposed that polygonization in the bondings near the defect is the reason for the crack growth. The grad fixed that found local grain refinement near the initial defect. Hong justified this local grain refinement through the numerous cyclic plexing theory. For example, Murakami, this is a very known theory, measured the high quantity of hydrogen near the initial defect and justified the crack growth due to the hydrogen embrittlement which is near the initial defect. Shirzawa finally proposed the carbide degradation model. But as can be seen, unified theories is not still present. But all researchers agree on two key aspects. FJ consumes more than 95% of the various cycle fatigue life, and therefore it plays the major role in the crack nucleation in the various cycle fatigue, and FJ force due to weakening mechanisms that permit the crack growth with stress intensity factor below the KTH. With regard to the second aspect, a general macromechanical model for crack growth in various cycle fatigue is here presented and discussed. In the following, we denote the stress intensity factor associated to the defect with K and the threshold for crack propagation as a threshold, global threshold. The original expression were obtained by Murakami through a lot of experimental results. The crack could not, according to this figure, the crack could not propagate since K is below the global threshold, And crack could propagate only if the defect is large enough to have a K which is larger than the global threshold for the material. Therefore, in order to let the crack grow, it is necessary to assume that the local threshold near the initial defect and below the K associated to the defect is present. In this way, the crack could propagate from the defect up to the border of the FGA with a K which is below the local threshold, and then from the border of the FGA the crack could propagate with a K which is larger than the global threshold, so with ordinary mechanism. Here we propose a very easy formulation for the local threshold. The local threshold is obtained as the global threshold minus a reduction stress intensity factor, which will be called a reduction K, and which account for the weakening mechanism that we discuss together, we propose together. The formulation that we propose for the K reduction is very simple and is based on very simple assumption. It must fulfill the dimensional homogeneity. It can be dependent on it can depend on the defect size, and it is proportional. It must be proportional to the initial defect size. The easiest formulation is reported on the slides, and it is a quite general formulation, since depending on the value of the exponent alpha, it can keep constant. The K reduction can keep constant, can increase or can decrease with the defect size. Through easy passage that we don't present for the sake of brevity, it can be shown that we can obtain a very easy formulation for the fatigue limit from defects, and it can be also demonstrated that both for alpha positive and negative, the formulation is the same. It is worth to note that this formulation is in agreement with the well-known formulation proposed by Murakami, and, but in this case, different from Murakami formulation, the constant coefficient must be estimated from the experimental data, and so estimated for every material tested, and the parameter estimation can be obtained in different ways. Here it will be obtained by through consideration of the crack growth rate within the FGA. Crack growth rate is generally modeled with Paris law, also in very high cycle fatigue, and three stages can be present in the sigmoidal crack growth rate diagrams related to very high cycle fatigue failures. The first stage is the below threshold region within FGA. The second stage is the steady crack propagation stage outside the fisheye and up to outside the FGA and up to the border of the fisheye. And the third stage is the stage of correspond to the stage of unsteady propagation. The crack growth within the FGA is obtained through a modified Paris law. This formulation is proposed in literature, but different from the literature, we proposed to use the local threshold in place of the global threshold, in order to take into account the weakening mechanism that we discussed before. The crack growth within the fisheye is obtained through Paris law, and also the crack growth beyond the fisheye is obtained through Paris law. The unknown parameters in the fatigue limit can be estimated through consideration of the crack growth within the FGA. Indeed, the number of cycles consumed within the FGA can be estimated experimentally, and can be computed as the difference between the total number of cycles to failure minus the number of cycles in stage 2 and stage 3, and also it can be computed analytically through an integration of the modified Paris law. But this equation depends on the unknown parameters. Therefore, one way for parameter estimation is through a minimization of the difference between the experimental number of cycles within stage 1 and the analytical number of cycles in stage 1. The coefficient that permit for minimizing this difference can be used for the estimation of the fatigue limit, and then the fatigue limit can be used for design purposes. The applicability of this model and this procedure is verified experimentally. We perform experimental tests on an H13 steel, whose characteristics are reported on the slide, and on the Gaussian specimen, which we designed and we proposed in previous IGF meetings, which permits to enlarge the risk volume of specimen tested in through ultrasonic tests. Experimental tests are performed by using the two ultrasonic testing machine developed at Politecnico di Torino, ultrasonic at loading frequency of 20 kHz tension compression test, it means stress equal to 0 are performed, and the tests are performed at constant stress amplitude to a closed loop control. Intermittent tests, which alternates pulse phase and cooling phase, are performed in order to keep under control the temperature of the specimen, and the temperature is always maintained below about 323 Kelvin. Vortex tubes are also used to reduce specimen heating and to speed up the cooling phase. Here the experimental results are briefly presented. We obtained 12 experimental failures and failures which are not presented on the SN diagram because are not considered in the analysis. And all the fractal sulfates originate from internal inclusion, non-metallic inclusion. We observe all the fractal sulfates using the SEM microscope and show efficient morphology. Here we take into account the global pressure for crack propagation. Indeed, as said before, the stress intensity factor computed at the board of the FGA must be equal to the global pressure, because outside the FGA the crack propagates according to ordinary mechanism and through the current to Paris law. As can be seen in the figure, the global pressure follows a linear trend with respect to the size of the FGA in a log-log plot. This is in agreement with the experimental results because the range found is the same range found in the literature for the same type of high-strength steels, and this behavior, this trend, is the same proposed by Murakami for high-strength steels with the same weaker hardness. Here we present the ratio between the number of cycles consumed within the FGA estimated, computed experimentally with respect to total number of cycles. It can be seen that this ratio increases with the number of cycles, and more than 99% of the fatigue light is consumed in the FGA formation. And this is in agreement with the experimental results. Here we report the average crack growth rate, which is computed according to the formulation reported on the slides, and the average crack growth rate is reported with respect to the number of cycles. As according to the literature, this value decreases with the number of cycles, but the most important aspect that must be underlined is that the crack growth, the average crack growth rate is below the physical threshold which is proposed in the literature and generally accepted in the very cycle fatigue literature. And this suggests that the crack alternatively arrests and grows with a mean value which is below the physical threshold. And this is a very important result that we can highlight from this investigation. Here, finally, we present the parameter estimation. The parameter estimation is obtained through a nonlinear optimization obtained by using the macro software. And as can be seen, the estimated value are close to the experimental value, both for the number of cycles and for the average crack growth rate. Indeed, they are close to the B-sector. Given these parameters, we can estimate finally the fatigue limit. Here we report the fatigue limit with respect to the inclusion size, and according to the literature, the fatigue limit decreases with the initial defect size, and as expected from its definition, the fatigue limit is far below the stress amplitude that induces failures for the investigating material. Therefore, we prove that the model that we propose and the procedure that we also propose for the estimation of the parameter allow for a conservative estimation of the fatigue limit, and therefore that can, in this case, can be used for design purpose. To conclude very briefly, a simple general formulation for the reduction of the stress intensity factor threshold is proposed, and this model permits to model all the weakening mechanisms involved in the FGA formation. A general expression for the fatigue limit and crack growth rate model is also proposed and defined, and this model were successfully applied to an experimental data set and validated, and we obtain a very conservative fatigue limit that can be used for the design purpose. Moreover, another result that we obtain and that confirms the experimental data reported in the literature and the average crack growth rate can be below the physical threshold, but this means that crack does not grow uniformly within the FGA, but it alternates unrest and propagation phase with a mean value that can be below the physical threshold. Thank you for that.